Hello, a very good morning to all of you. And uh, in this video, I'll be talking about the two important properties of Pauli's spin matrices. As you know, we have been talking about Pauli's spin matrices from last couple of lectures. So in this video, I'll be talking about the two important properties of these Pauli's spin matrices, and one is the commutation between the Pauli's spin matrices. We have the structure of these matrices already intact, sigma x, sigma y, and sigma z. And what we'll do is we will try to see that how the two spin matrices commute with each other or anti-commute with each other. But before going into the mathematical strangulation, let me introduce you with commutation and anti-commutation, and let's get an idea about the commutation and anti-commutation between the two physical quantities, between the two operators generally in quantum mechanics. So this is my title slide. I'll be talking about the significance of commutation and the anti-commutation relations in quantum mechanics. So to start with, in order to introduce you with the topic, what we have in quantum mechanics, what we do is we use operators to describe the physical observables. So here what we have the quantum mechanical operators. We utilize them to describe the physical observables. And what we have, the commutation and anti-commutation relations. These operations, these mathematical operations, what they do is they determine the fundamental structure of the quantum theory. So somewhere you have two operators. If they commute, then certainly you have a relation between the two operators. So this is how we introduce the commutation and anti-commutation relations, because they are leading us to the fundamental structure of quantum theory. So what we have operators in general. Talking about the simplest operators, what we have, the operators act on our eigenstates. They operate on the wave functions, and what they do is they extract the physical quantities. When you operate your operator on a wave function, what you obtain is a physical quantity, and there we have these two simple operators like position operator, momentum operator, and spin operators. Now, what do we mean by commutation? So what we have, if we have two operators, and say I have an operator A and an operator B, and if I have to find a commutation relation between these two operators, the commutation relation can be obtained by simply writing down AB minus BA. So what we have to do is we have to calculate AB, then we have to subtract this AB with BA. So A and B are two operators. Now, depending on your operators, the two operators can commute. If they commute, then the subtraction between these two will be equal to 0. So if they commute, what it means, the two observables, the two physical quantities that you have associated with these observables, you can exactly simultaneously calculate these two physical quantities. But if the subtraction AB minus BA is not equal to 0, so here what we say is, we say that these operators do not commute. and it automatically becomes an essence of Heisenberg's uncertainty principle. So these commutation relations are basically leading us to the Heisenberg's uncertainty principle. So suppose if I take a commutation between the position and the momentum operators, they will not commute. So you will come up with something in the right-hand side, leading us to realize that the two physical quantities that will measure by acting these operators on the eigenfunction will lead us to an uncertainty. So this is what commutation relations are, and what is the physical meaning of this commutation, as I was talking about, is if you have non-commuting operators, what they do is they simply imply Heisenberg's uncertainty principle. You have more certainty in measuring one, leading to the less certainty of measuring another physical quantity. So Heisenberg's uncertainty principle, if I calculate the commutation relation between the position and the momentum, what it does, it leads to IH cross, where H cross is the reduced Planck's constant. So what does this commutation mean? It simply means the Heisenberg's uncertainty principle. Delta x dot delta p is greater or equal to h bar by 2. Now, what we have in classical mechanics, if we have to realize a system, if we have to realize the evolution of a system, in classical mechanics, what we have is the Poisson brackets. And since classical domain is a domain of continuity, and these Poisson brackets, they have, what we do is, when we move from classical world to quantum world, what's happening is you're moving from continuity to discontinuous energy. Continuous system to a discontinuous system. So making a replica of Poisson bracket in the quantum mechanics, the Poisson brackets lead to commutators. It leads to these commutation relations where our framework is based on the quantization rules. So what we say here is commutation relations are used to quantize the classical systems. So this is the first important point. The canonical quantization, what it does basically, it replaces your Poisson brackets. It replaces the Poisson brackets with these commutators. Because in classical, what we have observables. In quantum, we have operators. And there is a relation between a Poisson bracket leads us to something 1 by IH bar times the commutator in the quantum mechanics. Now, angular momentum is another example. If we look at the components of angular momentum, they also don't commute. So what we have, we have done it in our previous course. If you calculate the commutation relation between Lx and Ly, it will lead us to IH cross Lz. So there happens to have these cyclic permutations between the operators. So finding a commutation relation between Lx and Ly, Lx being the x component of the angular momentum, orbital angular momentum, and Ly being the y component of orbital angular momentum. So it leads us to that cyclic permutations and defines the algebraic structure of the angular momentum. These commutation relations of these angular momentum components, what they do is they create a basis of that algebraic structure of angular momentum. Now, this was about commutation. Now let's talk about the anti-commutation relations. So for anti-commutation relation, if I take the same operators, A A and B, and you should, I have not put a cap on A and B, but I'm talking about that these two, A and B, they are the operators. These are quantum mechanical operators. And if you write down the anti-commutation between A and B, you will find the difference between the commutation. In case of calculating the commutation between A and B, we had a minus sign between the two. But here, for anti-commutation, we have a plus sign. So what anti-commutation relations are used for? They're primarily used for fermionic operators. For example, spin-half particles. Now, these anti-commutator, because the basis of anti-commutation is basically that your system should not violate the Pauli's exclusion principle, because you cannot have two particles in the same quantum state. So in order to adjust this thing mathematically, in the mathematical theoretical formalism, what we do is we introduce anti-commutators. Because using anti-commutators, we have two operators here. We have a creation operator and we have an annihilation operator. Now suppose in our mathematical framework, what we do is we have two fermionic particles, because anti-commutation relations are valid for fermionic particles, and fermionic particles, we do understand that if you have to sequence them in a system, you have to sequence them in accordance with the Pauli's exclusion principle. And this principle tells us that you cannot have same fermionic particles in the same quantum state. So if there arises a mathematical solution where you have two quantum particles trying to achieve the same quantum state, what we do there, we make use of these annihilation operators and creation operators. So these operators balances the situation of the particles in our quantum system. So this is anti-commutation. So fermions and spin. So what I was saying is that these fermionic creation and annihilation operators, what they do is they obey these anti-commutation relations. And what they do, what anti-commutators do is they ensure that the Pauli's exclusion principle is valid. That means no two fermions can occupy the same quantum state. So to conclude this introduction, we have commutation and anti-commutation relations, and they are basically very central in the quantum theory. And what they do is they define uncertainty. They are used to achieve the quantization and the statistics of the fermionic particles, especially in case of anti-commutators. And for commutation, what we have is we have this Heisenberg's uncertainty principle. Now let's go with these two important properties of Pauli's spin matrices, because we have already talked about some other important properties of Pauli's spin matrices, but now we will lead our discussion to the commutation and anti-commutation of Pauli's spin matrices. So let me write down these matrices first. What we have is we have sigma x, and this sigma x is 0, 0, 1, 1, and then we have sigma y, and this sigma y is 0, 0, minus I, and then I have sigma z, and the sigma z is 1, minus 1, 0, and 0. These are our Pauli's spin matrices, and I want to calculate the commutation and anti-commutation relation between the Pauli's spin matrices. So let's go with commutation relation first. Commutation relation. So what I have two operators. Say I have sigma x as an operator and I have sigma y as an operator. They are 2 by 2 matrices. So I want to calculate the commutation relation. So what you have to have these parentheses outside these two operators, and these brackets are indicating that you are going to calculate the commutation relation between sigma x and sigma y. So as I had shown in the slide, if I have A operator and B operator, if I want to calculate the commutation relation, then this commutation is simply AB minus BA. So here what we have sigma x and we have sigma y. And for sigma x, what will be the commutation? It will be sigma x and sigma y, then minus sigma y and sigma x. So what we have to do is we have to calculate sigma x, sigma y, then we will calculate sigma y, sigma x, we will subtract the two. That will lead us to the commutation between sigma x and sigma y. So to proceed on from here, I will be first calculating sigma x and sigma y. So for sigma x, what I have 0, 0, 1, and 1. This is sigma x. And for sigma y, I have 0, 0, minus I, and I. Now let's multiply these two 2 by 2 matrices and get the result. So here I'll have 0. So this will give me 0 and this will give me I. So this is 0 plus I, and this will give me 0, and this will give me 0. So this is 0 plus 0, and this will give me 0 and 0. So here I have 0 plus 0, and then finally what I'll have, this will give me minus I and plus 0. So sigma x and sigma y is going to be equal to a 2 by 2 matrix I, 0, 0, and minus I. So this is the first result. Now the next result is I want to calculate sigma y and sigma x. So this is my next target. Now for that, this will come first. What I'll have 0 minus I, and 0. You multiply this with 0, 0, 1, and 1, and this will lead us to, so this will give me 0 and minus I. This is 0 and minus I. The next term will be 0 and 0. So this will be 0 plus 0. Now the next is I. This is 0 and this is 0. So you'll have 0 plus 0. And the last will be I plus 0. So I plus 0. So what we have obtained sigma x, sigma y. Now we have obtained sigma y, sigma x, and we are going to subtract the two, because once we subtract the two, this will lead us to the commutation relation. So what we have I minus I, 0, 0. So the commutation between sigma x and sigma y is I, 0, 0 minus I. So this is I, 0, 0 minus I, and minus I, 0, 0. Minus I, 0 and 0. Right? So now what we have to do is we have to subtract these 2 by 2 matrices, and we will get the commutation between sigma x and sigma y. So what this will lead us, so I minus minus, so this will become plus, so you will have 2I here. And the next term, 0 will be added to 0, here you will have 0. The next element, and here again you will have 0. Now here what I have is minus I, and then this is minus I, so this will give me minus 2I. Alright? So what we can see, we can get this 2I out. 2I will be out, and something, or, okay. So this is going to be minus I, and this is, so this we can write 1, 0, 0, and minus 1. Okay? So sigma x and sigma y will lead us to 2I. And what is this? This is sigma, this is sigma z. Exactly, this is a sigma z. And we should check it out. Let us check it out. Yeah, come on. Sigma x, sigma y, and sigma z. 1, 0, 0, minus 1. So what is happening? Sigma x and sigma y, they don't commute. They don't commute, so you have sigma z. And what we can do is, we can generalize it. So sigma x and sigma y has led us to 2I sigma z. And if I go on with sigma y and sigma z, if I go with the commutation of sigma y and sigma z, this will lead us to 2I sigma x. Alright? So we can generalize this commutation between the Pauli spin matrices as, if we can take off sigma I and sigma j is equal to 2I sigma k. Alright, so if I takes the value of x, j takes the value of y, then the k will take the value of z. So what has happened here, what we see here is that the components of the Pauli's spin matrices, these matrices do not commute. So you don't have the exact certainty if you measure sigma I and sigma j simultaneously, because it's taking us somewhere close to that uncertainty principle. So this is the commutation. So what we have done here is we have found the commutation relation between the Pauli spin matrices. The Pauli spin matrices. Okay, so this is the point number 1, and this property has been divulged, it has been structured, and it has been mathematically realized. Now let's go with the anti-commutation relation. So anti-commutation. Now for anti-commutation, I will use the curly brackets. So for anti-commutation, sigma x and sigma y. So in order to calculate the anti-commutation, what we need is sigma x and sigma y. Then all we have to do is to add this with sigma y and sigma x. This is how this is done. And what we can do is we can calculate this anti-commutation between sigma x and sigma y. And I think we have already calculated this product, and we have also calculated this product. So what was the result of the first product? Now let's check that. What was that? Come on, come on. So that was minus I and I. For the reverse, what was it? No, this is for sigma x, sigma y. No, what was sigma y, sigma x? So this was sigma y, sigma x. So minus I and I is here. And here I have I and minus I. I and minus I. And you can see that. So here, what I have is I have I 0 minus I and 0 plus minus I 0 0 and plus I. Now all you have to do is to add these two matrices, the 2 by 2 matrices, and what we have we can add them. So I plus minus I will lead us to 0. This will lead us to 0. This will lead us to 0. Then minus I to plus I will lead us to 0. So what is happening? We are obtaining an anti-commutation relation between sigma x and sigma y, and this commutation leads to what is called as 0, 0, 0, 0, and you call it 0. So the same story will be true for sigma y and sigma z. So sigma y, sigma z will be equal to sigma x, sigma y, and x, y, y, z, zx. And this will be sigma z and sigma x. And the result of all these anti-commutation relations between the Pauli's spin matrices will be equal to 0. So what we can do here, we can generalize the result. So the first result for commutation relations of these Pauli's spin matrices, what we have sigma I and sigma j equals 2I sigma k. So for anti-commutation relation between these Pauli's spin matrices, what we have, they anti-commute with each other. So for that, what we have, sigma I, sigma j equals 0. Okay, now this is the one framework. Now if I calculate the same components that can be done, you can do that as well. You can calculate the commutation between sigma x and sigma x. This can be the first thing. So what will be the result here? We can see it. What is sigma x? It is 0, 0, 1, 1. Then multiply it by 0, 0, 1, 1. Then minus 0, 0, 1, 1. And again 0, 0, 1, 1. So we can see that the result here will be 0. So if you have same component of the Pauli's spin matrices, you can exactly calculate them. You can exactly measure them simultaneously. So what we will have, if I'm using the same component, sigma I and sigma I, this will automatically lead to 0. So what they do, they commute. The same component of the Pauli's spin matrices, they commute with each other. And doing the same exercise on the anti-commutation between this sigma x and sigma x. And for anti-commutation, what we'll have sigma x, then we'll have sigma x plus, then you'll have again sigma x, then again you'll have sigma x. And what you will do is you will multiply. So you will multiply. What is this? This is 0, 0, 1, 1. Then again 0, 0, 1, 1 plus again the same thing 0, 0, 1, 1 and 0, 0, 1, 1. Now we can calculate this, okay? So this is 0, 1. So this is 0 plus 1. So this is 0 and this is 0. So 0 plus 0. So this is 0, this is 0. This is 0 plus 0. This is 1 and this is 0. This is 1 plus 0. Okay? Then plus the same thing. So this will be 0 plus 1, 0 plus 0, 0 plus 0, and 1 plus 0. Okay, so what will this lead us to? This will lead us to the anti-commutation relation between the same component. And what will be obtained here is, this is 1, 0, 0, 1. Okay, 1, 0, 0, 1, and then plus 1, 0, 0, 1. So what will be the result here? So 1 plus 1 will lead us to 2, 0, 0, and 2. And what we can do is 2 can be out, and what will be inside will be 1, 1, 0, 0. Now what is this? This is sigma z. So the anti-commutation, so what this is equal to, this is 2 sigma z. So the anti-commutation between the same components, so the anti-commutation between sigma x and sigma x, it leads us to 2 sigma z. And the same thing can be generalized as we generalized the different components of the Pauli spin matrices. So what we conclude here, what we did here, we basically calculated the commutation and anti-commutation relation between the Pauli's spin matrices, the components of the Pauli's spin matrices, which are basically the quantum mechanical operators, and how their own implications in designing the quantum mechanical gates, where you can certainly go into the framework of quantum computer. And what we have seen that these Pauli spin matrices of different components, they do not commute, but the Pauli spin matrices of same components, they commute. And then there is a story of anti-commutation between these Pauli's spin matrices. So with this, I would like to conclude this talk. I hope you will like it, and you would like to share the videos if you find these videos are useful. So goodbye and good luck.